How Newton could decipher gravity was sufficient to allow us to fly from the Earth to the moon. Anyway, it kinda got to make you laugh to envision that you would have the option to go the whole way to the moon and back. That is, at last uses something I surmise. Everything in our universe seems, by all accounts, to be brilliant. There are guidelines governing the entire universe. Anyway, certain mysteries have remained bizarre regardless of numerous long periods of assessment. Why does time travel in one heading? What is the idea of reality? Why does gravity exist? Why does time dial down when we travel at the speed of light? These are questions that have enthralled us for quite a long time. Think about how conceivable it is that I let you realize that gravity is obviously misleading. It's simply a build of the human mind. This could appear to be faltering, but that is definitively what the famous physicist Brian Cox has recently guaranteed. How about we plunge into the idea of gravity and why time dials back to figure out what on earth is the matter with gravity? We, in fact, need to go past Newton. The issue lies not so much in what he got right, but in what he failed to address. There's an issue with Newton's hypothesis of gravity, and that will be that it essentially licenses us to foresee how things move under its impact. It doesn't say anything about why gravity exists or even how it works. It simply allows you to compute things. Newton knew this, obviously. He fundamentally recently said that it's down to God. In fact, he said that the most magnificent game plan of the sun, the planets, and the comets could proceed under the domain and direction of a wise being. As such, he gave us the tools to figure out how the objects move around, yet he said, "Don't ask me how or why, that is destined to be. That is down to God." In the huge universe that envelopes us, there are secrets keeping down to be uncovered. Among these mysteries are the surprising idiosyncrasies associated with time and gravity, two vital pieces of our reality. Envision a presence where time acts curiously, where it can slow down or accelerate, and where the power that keeps us grounded probably won't be what it seems, by all accounts, to be. This is the area of Albert Einstein's hypotheses of relativity, where how we might interpret time and gravity goes off in an unexpected direction. Albert Einstein, a name known to many, gave us a new perspective on the universe with his speculations of relativity. His work laid the foundation for how we could comprehend how time acts under different conditions, particularly when we travel at incredible velocities. Everything began during the 20th century when Einstein proposed two vital hypotheses: the special hypothesis of relativity and the general hypothesis of relativity. The special hypothesis of relativity, published in 1905, changed how we figure out existence. In basic terms, it lets us know that the laws of physics remain the same for all non-accelerating observers, regardless of their motion. This hypothesis presents the idea of relativistic effects, including the notable thought that time can extend or dial back under certain conditions. One of the most enchanting psychological tests used to make sense of time dilation is the light clock. Envision being inside a spaceship moving at an incredible speed, near the speed of light. Inside the spaceship, there's a light beam bouncing between two mirrors, perpendicular to the direction of motion. To an observer inside the spaceship, the light appears to travel straight. However, to an external observer who's not moving with the spaceship, things appear different. They see the spaceship moving at high speed and notice the light beam needs to cover more distance to reach the mirrors. According to the laws of physics, the speed of light is constant for all observers, so the light beam should appear to travel a longer, skewed path. Now, here's where it gets fascinating. The time it takes for the light beam to travel its way should be the same for both observers, the one inside the spaceship and the one outside. Anyway, since the path is longer for the outside observer, it seems like it would take some margin for the light to complete its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time dials back for the observer moving relative to the stationary observer. So in this present circumstance, time acts in an unexpected way. It relies upon your motion, and it's not simply a thought. Tests have confirmed these relativistic effects. For example, particles in particle accelerators like the Large Hadron Collider can reach speeds close to the speed of light. Researchers have to account for the effects of time dilation to make exact predictions and measurements. The special hypothesis of relativity opens up a reality where time is not a constant but can be extended or compressed depending on your motion. It challenges our ordinary intuition and drives us to the realization that the universe works in ways far beyond our common experience. Einstein's special hypothesis of relativity, introduced in 1905, reshaped how we might interpret the universe's texture, particularly in terms of time and motion. This hypothesis, in its essence, reveals that the laws of physics apply consistently for all non-accelerating observers, regardless of their motion. To grasp the special hypothesis of relativity better, we need to dissect its core ideas. One of the head thoughts of the special hypothesis of relativity is that the speed of light is the same for everybody, regardless of their motion. Whether you're standing still or moving at high speed, light continuously appears to go at the same constant speed, about 299,792,458 meters per second. This thought clashes with our standard experience, where speeds often add up. It's as though the universe has an intrinsic speed limit, and that speed is the speed of light. In special relativity, what we consider simultaneous events may not be simultaneous for everybody. If two events occur at different locations and you're moving relative to those events, what you see as happening simultaneously may not be simultaneous for another person at a different vantage point. This seemingly impossible idea challenges our traditional concept of time. The idea of time dilation is perhaps one of the most dazzling and substantial implications of the theory. As mentioned earlier, time can slow down or stretch depending on your motion. The faster you move, the slower time appears to elapse for you compared to a stationary observer. This effect becomes more pronounced as you approach the speed of light. Envision two indistinguishable twins, one on Earth and the other traveling into space at a significant fraction of the speed of light. When the space-traveling twin returns, they will be younger than their terrestrial sibling. This phenomenon, often referred to as the twin paradox, is a genuine outcome of time dilation. The reason for this surprising behavior lies in the invariance of the speed of light. As the space-traveling twin approaches high speeds, their clock appears normal to them. However, to an observer on Earth, the space-traveling twin's clock appears to slow down because the twin is moving relative to the Earth. Another result of special relativity is length contraction. As an object moves at high speeds, its length along the direction of motion appears shorter to a stationary observer. This effect is minor at ordinary speeds but becomes more noticeable as an object approaches the speed of light. One of the most famous equations in physics, E=mc², is a direct consequence of special relativity. This equation states that energy and mass are interchangeable. It implies that mass can be converted into energy and vice versa. This principle is crucial in understanding the behavior of particles at high speeds and the energy released in processes like nuclear reactions. Special relativity isn't just a theoretical concept. It has real-world applications. For instance, GPS systems depend on the precise timing of signals from satellites. However, because these satellites are moving relative to us, time dilation effects come into play. If the effects of special relativity weren't accounted for in GPS calculations, our navigation systems would be significantly less accurate. The special hypothesis of relativity drives us to rethink our intuitive ideas of reality. It shows that the universe operates in ways that defy ordinary experience. Time is not an absolute concept but is relative, influenced by motion. The constancy of the speed of light and the relationship between energy and mass are central ideas that have been confirmed by various experiments. Now let's delve into the general hypothesis of relativity, another remarkable idea put forward by Albert Einstein in 1915. This theory takes us into the realm of gravity, revealing a significant connection between gravity and the actual texture of the universe. At its core, the general hypothesis of relativity challenges the traditional notion of gravity as a force that acts at a distance between masses. Instead, it presents gravity as a result of the curvature of spacetime. This idea is more straightforward than it might sound. To understand general relativity, we need to consider the universe as a four-dimensional entity, combining 3 dimensions of space with 1 dimension of time. In this four-dimensional spacetime, massive objects like stars, planets, and even you cause the fabric of spacetime to bend around them. This curvature is what we perceive as gravity. Envision spacetime as an immense, flexible fabric. A massive object like Earth creates a dimple in this fabric. When you place a smaller object like a ball near Earth, it rolls toward the dimple. This is similar to how an object falls under the influence of gravity. It's not a mysterious force. It's simply following the shape of spacetime. General relativity provides a robust explanation for the motion of celestial bodies in our solar system. It accurately predicts the orbits of planets, such as the elliptical path followed by Earth around the Sun. The old idea of gravity as an attractive force didn't fully account for these orbital movements, but the concept of curved spacetime does. One of the most striking confirmations of general relativity came during the solar eclipse of 1919, when Sir Arthur Eddington led an attempt to observe the bending of starlight by the Sun's gravity. According to the theory, the Sun's massive presence would bend the path of light from distant stars, causing them to appear slightly shifted from their usual positions. Eddington's observations matched Einstein's predictions, providing solid evidence for the curvature of spacetime. Another captivating prediction of general relativity is the existence of black holes. These are regions of spacetime where gravity is so strong that nothing, not even light, can escape. Black holes arise naturally from the conditions of general relativity when a massive star undergoes gravitational collapse, creating a singularity of infinite density surrounded by an event horizon beyond which nothing can return. Recently, we've obtained direct evidence of black holes through observations of gravitational waves, ripples in the fabric of spacetime caused by the acceleration of massive objects. When two black holes merge, they produce gravitational waves that travel through the universe. The detection of these waves by observatories like LIGO, Laser Interferometer Gravitational Wave Observatory, has confirmed the existence of black holes and provided further support for general relativity. One of the more mind-bending aspects of general relativity is the concept of time dilation near massive objects. Just as time slows down when we move at high speeds, it also slows down in strong gravitational fields. This means that time passes more slowly for an observer near a massive object compared to someone farther away. This effect, known as gravitational time dilation, has been observed and measured. For instance, precise atomic clocks set at different altitudes show that time runs slightly faster at higher elevations where the gravitational pull is weaker. The implications of general relativity are not limited to extreme astronomical phenomena. They also play a crucial role in understanding the large-scale structure of the universe. The expansion of the universe, first observed by Edwin Hubble, is explained by the general hypothesis of relativity. The theory describes how the fabric of spacetime itself can stretch and expand, carrying galaxies along with it. The general hypothesis of relativity has revolutionized our understanding of gravity and the universe. It reveals that gravity is not a mysterious force acting at a distance, but a consequence of the curvature of spacetime caused by massive objects. This elegant idea has been confirmed by various observations and experiments, from the bending of starlight to the detection of gravitational waves. The concept of gravitational time dilation further emphasizes the interplay between time and gravity. Einstein's theories have transformed our view of the universe, offering profound insights into the nature of reality. While they may not provide all the answers, they have opened new avenues of exploration and inquiry. Einstein's theories challenge us to reconsider the fundamental nature of space, time, and the universe itself. They suggest that our intuitive understanding of reality may be limited and that the universe operates in ways that defy our everyday experience. The theories of relativity remind us that scientific knowledge is a journey of discovery, where each new finding leads to new questions and deeper understanding. In conclusion, Newton's hypothesis of gravity laid the groundwork for understanding celestial mechanics, but it was Einstein's theories of relativity that transformed our grasp of gravity as an inherent property of spacetime. The special hypothesis of relativity introduced the concept of time dilation and the constancy of the speed of light, challenging our notions of time and simultaneity. The general hypothesis of relativity further advanced our understanding by describing gravity as the curvature of spacetime caused by mass and energy. This idea not only explained gravitational phenomena such as planetary orbits and the bending of light, but also predicted intriguing phenomena like black holes and gravitational waves, which have since been observed. Einstein's theories continue to inspire and guide researchers in their quest to comprehend the universe at both the largest and smallest scales, revealing a cosmos where existence is interwoven and where gravity is a manifestation of the geometry of spacetime itself. As we continue to explore and test Einstein's theories, we are reminded that the universe is full of mysteries waiting to be unraveled. Each new discovery brings us closer to understanding the secrets of the universe and our place within it. How Newton could decipher gravity was sufficient to allow us to fly from the Earth to the Moon. Anyway, it kind of makes you laugh to envision that you would have the option to go the whole way to the Moon and back. This ultimately uses something, I guess. Everything in our universe seems to be brilliant. There are guidelines governing the entire universe, yet certain mysteries have remained bizarre regardless of numerous long periods of assessment. Why does time travel in one direction? What is the idea of reality? Why does gravity exist? Why does time dial down when we travel at the speed of light? These questions have enthralled us for ages. Consider the possibility that I let you know that gravity is actually misleading. It's simply a construct of the human mind. This may seem staggering, but that is precisely what the famous physicist Brian Cox has recently asserted. Let's delve into the idea of gravity and explore why time dials back to figure out what is fundamentally at stake. We need to go beyond Newton. The issue lies not so much in what he got right, but in what he failed to address. There's a problem with Newton's theory of gravity. It essentially allows us to predict how things move under its influence, yet it doesn't say anything about why gravity exists or even how it works. It simply provides tools for computation. Newton was aware of this, of course. He essentially said it was down to God. He posited that the most magnificent arrangement of the sun, planets, and comets could proceed under the domain and guidance of a wise being. In that sense, he gave us the tools to understand motion but advised us not to ask how or why. Those questions were beyond our reach, left to divine explanation. In the vast universe around us, secrets are waiting to be uncovered. Among these mysteries are the curious quirks associated with time and gravity, two vital components of our reality. Imagine a world where time behaves strangely, where it can slow down or speed up, and where the force that keeps us grounded might not be what it seems. This is the realm of Albert Einstein's theories of relativity, where our understanding of time and gravity takes a surprising turn. Albert Einstein, a name known to many, revolutionized our view of the universe with his theories of relativity. His work laid the foundation for a new comprehension of how time acts under various conditions, particularly when we travel at incredible speeds. Everything began in the 20th century when Einstein proposed two vital theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, transformed our understanding of existence. Simply put, it states that the laws of physics remain the same for all non-accelerating observers, regardless of their motion. This theory introduces the idea of relativistic effects, including the notable concept that time can extend or dilate under certain conditions. One of the most fascinating thought experiments used to explain time dilation is the light clock. Picture yourself inside a spaceship moving at incredible speeds, near the speed of light. Inside the spaceship, there's a light beam bouncing between two mirrors, perpendicular to the direction of motion. To an observer inside the spaceship, the light appears to travel straight. However, to an external observer not moving with the spaceship, things look different. They see the spaceship moving at high speed, and the light beam must cover a longer distance to reach the mirrors.